Hi, this is Ushendra. In this video, I'll be discussing something about time integration property in Laplace transforms. A very important property, extensive use in many courses. It may be you can find the application of this one. You're making use of this property in pulse and digital circuits, in control systems, many courses, right? A very important one. The simplification will be easy if you make use of this time integration property of Laplace transform. Going ahead, what is the Laplace transform? A given function x of t will be given. The Laplace transform of this function will be, its notation in frequency domain x of s. What it will be, how to obtain the Laplace transform of any given function. The given function multiplied with e raised to minus st and integrated with respect to t from 0 to infinity for a unilateral Laplace transform. It will be plus infinity to minus infinity for a bilateral Laplace transform. It depends, right? So going ahead, if this is the case, what will be the Laplace transform of integral x of t dt? What will be the Laplace transform? This is the given function, and if this is that case, so what will be the same thing? This function given integral x of t dt, this function, this function is multiplied with e raised to minus st and integrated from 0 to infinity, this one with respect to t, right? Here we can see like this is one, we can see two terms. This is one term 1 and this is another term, two terms, and under this condition integral of these two can be carried out with the help of UV rule. What according to UV rule it says, let me write on that side for small clarification here with another ink, don't get confused. Integral uv dt, that will be, according to the expansion goes like this one. Integral uv dt will be the first function as it is u, right? The first function as it is, integral of the second function dv dt, integral of the second function, and we need to plug in the lower and upper limits for this. In this case it's 0 to infinity minus, watch carefully, minus derivative of the first function multiplied by integral of second function, and what happens is this whole product is integrated again with respect to t. This is what it happens in UV rule. Making use of this one, going ahead, the computation will be easy if you make use of that UV rule, right? And in this case, let this be the first term u and let this be v, right? In that case, the Laplace transform of this one, Laplace transform of integral of x of t dt, that will be extending, making use of UV rule over here and going ahead, this one u as it is, that is integral x of t dt as it is, multiplied with the integral of the second term. The second term over here is e raised to minus st, and the integral of this will be with respect to t, integration with respect to t, and so this will be the variable and this will be the constant, and that comes down. The integral of this one will be into e raised to minus st upon, so this minus comes down because that is the constant in that case, and we need to plug in the lower and upper limits here. This is how we plug in, this is how we plug in. We cannot stop over here. Going ahead, minus the derivative of the first function. This is the first function. What is the first function in this case? Integral x of t dt is the first function, and the derivative of this function will be simply x of t. Why? Because we have an integral, and if the derivative of this one will be like cancelling, the derivative and integral gets cancelled and we'll be left with only x of t, and so we have only x of t, right? And integral of the second function, once again integral of second function, integral of e raised to minus st, and with respect to t again, so minus s comes down. And as I've told you, like in UV rule, this product should be integrated with respect to t once again. right? Integral 0 to infinity. In this case, we are from the beginning we stick to this 0 to infinity. So for a unilateral Laplace transform, and this is what, and we need to plug in the lower limit and upper limit. So doing that, what we have is plugging in the upper limit in wherever t should be substituted with infinity, and wherever we find t, we have to plug in with this one. So plugging in the upper limit, what we have is, here I'm plugging in the upper limit, integral x of t dt at t equal to infinity into e raised to minus s into infinity upon minus s. This is for the upper limit, and going ahead, minus plugging in the lower limit, integral x of t dt at t equal to 0 into e raised to minus s into 0 upon minus s, plugging in the lower limit 0. Wherever we have, that will be plugged in with 0. Yeah, 0. This is what. Going ahead, this comes down, minus integral 0 to infinity x of t e raised to minus st dt. Guys, this s has got nothing to do inside the integration. It's a completely different term inside the integration with respect to t. So this has got nothing to do inside, so we can take this out, and we have a negative over here, this negative over here, that becomes positive, minus into minus plus, and writing that s which is in the denominator outside the integration. So this is the simplification over here, right? And please watch here, this may be anything, x of t plugging in with infinity, but this one, e raised to minus s into infinity, this term will be infinity, e raised to minus infinity, right? E raised to minus infinity, that will be 0. Anything multiplied with 0, and we have 0. This complete term becomes 0. Why? Because I'm repeating, it may be anything, x of t may be anything, it may be given anything, but looking at this exponential very carefully, it's e raised to minus s into infinity, and this one becomes infinity, e raised to, and this totally becomes e raised to minus infinity, and e raised to minus infinity, it's a 0, right? And going ahead, here e raised to minus s into 0, that will be 1, and we'll be left with only this one. This becomes 1, this becomes 1, and we will be left with yeah guys, minus and minus, that will be positive, 1 upon s, this s I've written down over here, and in the numerator what we have is integral x of t dt at t equal to 0. This is what we are left with, and moving ahead, plus 1 by s, and guys, here you need to focus, x of t is multiplied with e raised to minus st and integrated from 0 to infinity with respect to t. Here x of t is multiplied with e raised to minus st and integrated from 0 to infinity with respect to t. So this term will be this. So we have x of s. This can be written as x of s, and a small, even more scrambling or reordering it, what we have is Laplace transform of integral x of t dt, don't get confused, it's x of t dt will be x of s upon s plus s in the denominator as it is, integral x of t, yeah, this is x of t dt at t equal to 0, right? At t equal to 0, guys, this second term will be the initial condition. It may be the initial condition of a capacitor or an inductor. It may be considered, may not be considered according to the requirement. For example, when we evaluate the transfer function in control systems or any other transfer function, when evaluating the transfer function, usually the initial conditions are neglected. So this is the initial condition. It may be of the capacitor or inductor. So it may be considered, it may be not considered according to the requirement. Now finally, this is the final reduction for a Laplace transform of integral of x of t, integral property of Laplace transform. Time integral, yeah, integration is done with respect to time, and so it's a time integral property of Laplace transforms. Hope you understand this video. If you find this useful, please share, please subscribe my channel Ushendra's Engineering Tutorials. This is all for today's video. Thank you so much. Stay home, stay safe.